Hello. I want to go over this leak code question that I did today. And it involves finding if the leaf nodes are similar in within a tree. So, or within two trees. So what we're doing is we're comparing two trees and then finding out if the leaf nodes are equal to each other, and if it's in the same order. So, um, a leaf node is defined as as a node that doesn't have any other nodes connecting to it. So five wouldn't be a leaf node because it is connecting to six and seven. Six is a leaf node because it's connecting to nothing, and so on and so forth with all these other highlighted ones. So yeah, that's just a quick background of what this problem is asking for. Um, so yeah, let's get to it. Um, Class solution. This is how LeetCode defines um, the solution for their problem. So class solution, it would be a bool. So either return true or false. Uh, what is it? Similar leaves. I think they called it similar leaves. I think I spelled that wrong, but it's okay. And we would be passing a tree node um pointer root one and a tree node pointer root. But before we get up into this, we're going to create a helper function that's going to collect all the leaf nodes from both trees. So this would be type void, and we're going to call it collect. Oop, collect leaves, and we're going to pass in a tree node um, pointer root, and then a vector of type int, and we're going to reference this and just call it leaves. Um, so what this function is going to do is going to traverse through the tree, find a leaf node, and then input that leaf node into the vector of leaves. So first we're going to say if root is equal to null pointer, we want to return. And then our next if statement is if root left is equal to null and root right is equal to null. What we want to do is push back that current node's value into the vector of leaves. So leaves dot pushback root value. Okay, and then we want to recursively check the left side of that root, left, and the right side of that. Sorry. Recursively check the left side of the current root until we reach the leftmost root, and then recursively check the right side of our current root until we reach the rightmost uh, a leaf node. And we're going to be passing um, the same vector of leaves into this so we can keep track of it. So essentially, this is it for our uh, helper function to collect the leaves. I'm gonna just call this private though for now. Private because I don't want I don't want the main to be able to access it just within the class. Um, so in here, what we're gonna do is declare two vectors of type int. Leaves one is gonna be in charge of holding all the leaf nodes for root one, and then uh leaves two is going to be in charge of holding all the leaves for root two, of course. And now we just call the function on both root one and leaves 1. Um, and then call the function on root 2 and leaves 2. And then what we return is if leaves 1 is equal to leaves 2. So what this is returning is if the elements within vector leaves 1 is equal to the elements within vector leaves 2. So let me just show y'all what exactly is really happening. I'm using my tablet again, so um, don't mind if I'm like kind of chopped with it. Um, so in here, we're going to declare can I highlight this? I don't know how to highlight it, but we're going to declare leaves 1 and leaves 2, right? And then we're going to call collect leaves um, with root 1 and leaves the vector leaves 1 first. So we're going to enter this collect leaves function with root 1 and leaves 1 to begin with. So what we're doing now is we're checking if the root is null. If it is, we return. In this case, 3 is not null. So we move on to this, check if 3's left and right is null. In this case, we have 5 and a 1. It is not null. We don't enter either of the if statements. We now recursively check the left side of this root right here, our main root, which is 3, and we pass in the we reference and pass in the vector of leaves 1 again um for this for our next node. So now our root is 5. Um, Now we check both if statements. Root 5 is not null, and root 5's left and right are not null as well. Recursively check the left side of 5. Now we're at root 6. Is root 6 null? No. Um, Now we check if um, root 6 is left and right is null. In this case, it is. So we're going to push back 6 into our leaves 1 vector. So I'm gonna just call it L1 for leaves 1 is equal to here we already checked this guy is in fact a leaf node, so we can pass it into here. 6, that's a 6, okay. Now we return back to this node since we haven't checked the right side of 5 and we know that there's elements within 5. We can now check the right side of 5 because of this right here, this line. If I can highlight it, I can't highlight it, but this line. So now we're checking the right side of 5, which is 2. Now we check if 2 has a left side. In this case, it does. So we move on to the left side. Check if 7 has a left side. It doesn't. Return back to 7. Check if 7 has a right side. It doesn't. Return 7's left and right side is null. Now we can push that back into right here. We can push 7 into the leaves vector. 7. Now we go back to 2. We recursively check the right side of 2, which is 4. Recursively check the left side of 4. It's null. We return back to 4. Recursively check the right side of 4. It's null. We return. 4 is in fact a leaf node because both left and right are null. We can now push this back into a vector. So 6, 7, and 4 are now within the vector. Now we return back to 2. We already checked both the left side and right side of 2. Return back to 5. We already checked both the left and right side of 5. Return back to 3. We already checked all of the left side of 3. Now we have to check the right side of 3. We move on to 1. Check if 1 has a left side. It does. 9. Check if 9 has a left side. It doesn't. Return back to 9. Check if 9 has a right side. It doesn't. Return back to 9. We know that this is a leaf node because of this line again right here. So now we push 9 back into the vector. Now we can return back to 1, check the right side of 1, which is 8. check the left side of 8, which is null. Check the return back to 8, check the left side, right side of 8, which is null. Return back to 8. We know that 8 is a leaf node because both left and right are null. You what an ugly 8. Ew, what a worse 8. Sorry. Um, oh my lord. Oh my lord. Oh my lord. Sorry. Oh, oh, messing with me. This is an 8. Oh my god. 8. There we go. Um, so now we have a vector of um L1. So L1 vector is now equal to this right here, 6, 7, 8, 9. Now we're going to we did this part right here. Now we do the same thing with root 2, which is going to follow the exact same steps that I did for root 1. Recursively check the left side. If it's a null, move back up here, check the right side if it's a null. Put this into L2, which is leaf 2 vector. This would be 6, and then same thing, go back to 5, check 7, check 7's left and right. Doesn't have anything, push it into the vector. Move back up the tree. Now we're going to check the right side of 3. We check 1, 1 has a left side. We check 4, 4 doesn't have a left side. We check 4's right, 4 doesn't have a right side. Now we can push back 4 into the vector. And then we can now check the right side of 1. The right side of 1 is 2. 2 has a left side. We check the left side of 2. 9. We check the left side of 9. Nothing. We check the right side of 9. Nothing. We can push 9 back into the vector. Go back to 2. Check 8. 8 doesn't have a left or right side. We're able to push it back in. And boom. So now we have done both sides. And now we're going to compare if left is equal to leaves 1 is equal to leaves 2. In this case, it does because 6 and 6, same position, same number. 7 and 7, same position, same number. 4 and 4, same position, same numbers. 9 and 9, same position, same number. 8 and 8, same position and same number. So these two are equal to each other. It would return true. Yay. Um, but if say, let me go back. If we had, say, just in this example, 10 here, or no, let's say 10 here, because that makes sense right there. 8 wouldn't be the leaf node anymore because it has now like a child. It's pointing to 10. Um, Now instead of 8 being the last element in our um, L1 vector, it would be 10. 10. And then when we compare, everything would go nice and smoothly up until the last element, 10 and 8. Two different numbers, two different values for the node. This would, in fact, return false. This does not equal each other. So this would be false. So now let's show it the code. So we're going to declare solution. Ah, solution. I didn't spell it right. Oh man. Solution. We're gonna say bool. I'm gonna say equal leaves is equal to solution dot similar leaves. Pass in tree 1 dot get root, and then tree 2 dot get root, and then our leaves equal in both trees. Um, equal leaves. And then true, false. End line, end line, end line. So if we run it here, we can see that, let's run it again. We can see that it is true because, as you can see here, um, leaf node here is 0, 0. Leaf node here is 3, and leaf node here is 3 as well. It doesn't really matter where the position is. They're equal because um, there's just nothing else to, there's no other leaf nodes after 3 on both one. So that would be true. If we change, say, or if we added tree 2 dot add node 4, this would be false because the next node after 3 in our second tree is 4, whereas for this tree, our last and final leaf node is 3. This would be comparing 0 and 3. Um, this would be comparing, where is it? 0 comma 3, the vector 0, 3 for tree 1 would be comparing to 0 comma 4. And this is in fact not equal to each other. So it is false. Uh, yeah, sweet. Thank y'all for watching. Let me know if this was clear for you, or if you need any more clarification. Sorry for my bunk handwriting. Um, I'm still practicing on this little tablet that I bought. Anyways, thank you for watching.